When I first started 3D modeling with CAD software, I always struggled to create beautiful, realistic renders with animations that would truly showcase my hard work. In this video, I'm going to share the tutorial I wish I'd had when I was learning to render and animate. We'll be using the stem we modeled in the previous video. If you missed that one, you can find the 3D file we'll be using in this tutorial, along with all the necessary files, linked in the description. You can download the files for free on my Ko-Fi page, but if you'd like to support the channel, you can also purchase the files for any amount you choose. First, we'll export the 3D file from our CAD software. Then, we'll texture the stem by creating a simple yet effective material, while also adding a decal to the front part. Finally, we'll conclude the video with a simple but impactful animation that you've seen. Before starting to work on rendering and animation, we need to export the 3D model. To do so, select the assembly in the tree view, ensuring all elements are selected in blue in the viewport. Then go to File, Export, or use the shortcut Ctrl+E. Select the location where you want to save your model. Use a name that makes it easy to find the file. You must then choose an export format that will be readable by a rendering software. In our case, we will use Blender, which can open mesh file types such as .stl, .obj, .ply, or .gltf. As shown here, you can see the model exported in different formats. The .stl, .ply, and .gltf files are exported directly without remeshing, while the .obj file has been remeshed before export. We can see that the .gltf and .obj files have a better surface quality. Additionally, the .gltf format preserves the hierarchy of the tree view with separate bodies, and the file size is much more optimized. The only downside of the .gltf file is that the vertices are not merged, which can be problematic if you want to modify the file in Blender, but in our case, it doesn't matter. We will therefore choose the gltf extension for export. Now open Blender, and if you haven't downloaded it yet, hurry to the blender.org website to download this wonderful software. Blender is a free and open-source 3D creation software, offering a complete suite of tools for modeling, animation, rendering, simulation, compositing, and video editing. Although FreeCAD or Fusion 360 have rendering workbenches, if you want to create professional quality renderings and animations, you cannot rely solely on them and must use software such as Blender. Blender's interface can seem intimidating at first, but don't worry. If you're a beginner, I will guide you and show you that with a little knowledge, you can achieve very convincing results. To begin, to navigate in the 3D view, you use the middle mouse button click to rotate, Shift plus middle mouse button click to pan, and left click to select. Blender is software that is used extensively with keyboard shortcuts. I will strive to use the menus throughout, but if out of habit I use shortcut keys, you can follow the keys I press. They will be displayed in blue at the bottom right. In the center of the interface, you have the 3D viewport similar to CAD software. On the right side, you have the outliner or scene collection, which is like the tree view in FreeCAD, and below that, the properties editor. To begin, we will delete the point light as well as the cube. To do this, select the point light and, while holding down the Shift key, select the cube. Then go to Object and click on Delete. You can also use the X or Delete key on your keyboard. You see, so far, so good, right? To import our file, we will go to the File menu, select Import, and click on GLTF, which is at the bottom of the list. Then navigate to where you saved your file and select it. You can leave the default settings in the right-hand panel. Then click Import. Depending on your computer's performance, the import may take a while. Once the file is imported, you'll see a new line appear in the outliner on the right. This indicates that the object has been successfully imported. However, you might not see the object in the 3D viewport yet. Don't worry, this is normal. We're too far away from the object to see it. To zoom to it, go to View, Frame Selected. This will zoom directly to the object. Zoom out a little because we're now too close. Choosing GLTF imports our file with the correct scale, which isn't always the case with other file formats. In the outliner on the right, we can also see that the file retains the same hierarchy it had in FreeCAD. All the parts are separated, the stem and the 6 screws. However, because we're modeling this way in FreeCAD, the front part of the stem is part of the same mesh as the base. But in our animation, the front part moves independently of the central section. Our first step will be to separate these two meshes. With the stem 001 mesh selected, switch from Object Mode to Edit Mode using the menu at the top. You can also use the Tab key. This mode allows you to directly edit the 3D model by manipulating its vertices, edges, and faces. This is a completely different approach compared to CAD software, where mathematical operations are used to modify the object. Here, we edit it directly. To separate the front of the stem, we'll first align the view to be perpendicular. To do this, click the green axis handle in the top right corner. This will align the view perpendicular to the y-axis. The goal now is to select all the vertices on the right. A gap marks the vertices we need to select. To select all vertices, including those hidden behind, we need to switch to wireframe view. To do this, click the wireframe icon in the top right corner. This will allow us to see and select all vertices. We'll use the box select tool to select the vertices. It's usually selected by default, but if not, you'll find it in the toolbar on the left. Click and drag to create a selection box encompassing all the vertices on the right. Selected vertices will turn orange, and unselected ones will remain black. To separate the front part, go to the Mesh menu at the top, then Separate and choose by selection. This will create a new mesh, adding a new entry to the outliner. Switch back to Solid View to confirm the separation. You'll no longer see the selected vertices and edges. You can now exit Edit Mode and return to Object Mode. All parts are now properly separated into their own meshes. For better file organization, we can rename the two separate meshes using F2. The base to stem_base and the front part to stem_front. We have finished editing our solids. We will now move on to the most interesting part, which is the application of textures on the different meshes. To do this, we'll switch to the shading workspace. In this space, we'll be working with various materials and lighting to illuminate our object. As in the previous view, our object is zoomed out very far. To make it visible, select the assembly in the outliner and then go to the View menu and choose Frame Selected. This will center the view on the object. You can zoom out with the mouse wheel and use panning to orient yourself. Before we start, we need to adjust a few settings. First, in the Properties panel, go to the Render tab, the camera icon. We'll switch the render engine to Cycles. This engine provides the most realistic results. Next, if you have a dedicated graphics card, I highly recommend changing the device from CPU to GPU. This will significantly improve viewport performance. Then, in the viewport sampling section, I recommend setting the samples to 32, enabling denoising and choosing optics as the denoiser. If you don't have an NVIDIA card, you can leave it on automatic or try Open Image Denoise. These settings will give you a fast, noise-free viewport with a quality close to your final render, which is very helpful. Finally, in the render sampling section, I suggest setting the max samples to 1000 instead of 4096 to reduce future render time. This was the slightly less exciting but necessary part of the video. You could spend a lot of time finding the perfect settings to improve render quality and reduce render times. However, for a project, these settings are a good starting point. To switch to rendered view, simply click the rightmost icon at the top of the viewport. As you can see, the 3D view is now darker. This is due to the default dark gray world lighting. To change the lighting easily and effectively, we need to modify the world environment. You can find the world settings in the Properties editor on the right, indicated by the red globe icon. You can adjust the world color to see how the lighting responds by picking a lighter color. The light is better, but it's still quite flat and not ideal. To improve this, we'll switch from a solid color to an HDR environment. An HDR image is a 360 degrees image that creates realistic lighting. For beginners in rendering, this is an excellent way to get good results without having to set up artificial lights. To add an HDR to our scene, simply click the yellow dot next to color and select Environment Texture. You'll notice the environment turns pink, indicating that no HDR is currently loaded. To load your HDR, click the Open button. Navigate to where you save the file. You can find a link to the HDR in the video description. Select the file and click Open Image. The scene should look more realistic now. You can rotate the view to see your object and appreciate the new lighting. Now, we want to keep the HDR lighting, but remove the background. This is easy to do. Go to the Properties editor on the right and click the Render Properties tab, the camera icon. Scroll down to the Film panel and check the transparent box. The HDR background should disappear, leaving only your stem with the correct lighting. Now we'll adjust the stem's material to make it look more realistic. Select the base of the stem with your mouse. A new icon will appear in the Properties panel on the right, a red and black sphere. This is the Materials icon. Click it to open the Material Properties. In the menu that opens, you have access to the shader's core properties. First, let's adjust the color. Click the Color swatch. A color wheel will appear, allowing you to choose a color. We'll select a near black color. That's already looking much more realistic. Our material will be a black paint, meaning there won't be any metallic appearance. A metallic look is primarily used for raw metals like gold and copper, but it's not appropriate for our paint. So we'll adjust the value to 0. The next parameter is the roughness. The roughness defines how rough or smooth a surface appears. More specifically, it controls how light is reflected by that surface. A surface with low roughness, close to 0, reflects light specularly, like a mirror, creating sharp and bright reflections. Conversely, a surface with high roughness, close to 1, scatters light in all directions, resulting in a matte and diffuse appearance, without distinct specular highlights. We'll use a roughness value of 0.4 here, which will result in a somewhat reflective surface. We'll also adjust the color to get a deeper black. Now we'll create the material for the bolts. To start, select the bolt, and in the right menu, we'll adjust the color to approximate steel. We click on the color swatch to open the color wheel. We switch to RGB mode and enter the 367 for the red, 354 for the green, and 340 for the blue. Next, we'll adjust the roughness to 0.270 to achieve a slightly shinier look than the stem. Since the bolts share the same material, the shader is applied to all of them. We're starting to get a much better result, but to make it truly perfect, we still need to tweak some parameters, especially for the stem shader. Upon closer inspection of the model, we can see sharp edges all over. In real life, even intentionally sharp edges are not perfectly sharp. To fix this, we'll use a bevel, which we'll apply to the normal input in the right-hand menu. To add a bevel, with the stem selected, click the purple circle next to the normal input. The normal input allows you to add geometry to a flat surface without actually creating geometry. It simulates it. In our case, this will create fake bevels across the entire piece by creating shadows that mimic the shadows of a real bevel. In the drop-down menu that appears, scroll to the top to select Bevel. As you can see, nothing is showing up because the bevel radius is far too large. Set the value to 0.005, which corresponds to a 5 mm bevel. We can see an effect, but it's much too strong. Set the value to 0.0005. The result is already more convincing. Increase the sample value to 10 for an even smoother bevel. I still think the effect is too pronounced. I'm reducing the bevel size further to 0.0003. Now it looks good to me. This small detail really adds realism to the piece. I now like to change the HDR's orientation to get the shadows to reflect differently on the object. To do this, we need to use the Node Editor. The Node Editor really gives you complete control. It's admittedly more complex to use, but the results are spectacular. It can seem intimidating, but I'll guide you through it. The Node Editor is located in the bottom window, which I've just expanded. Currently, it's set to the stem shader. To configure it for the HDR, we need to switch the top left drop-down menu from Object to World. You can see that the HDR settings we entered in the right-hand menu have been converted into nodes. At the beginning of the node setup, you can see the HDR image, which is connected to a background node that extracts the HDR's lighting and background. This node is then connected to the World node, which creates the environment. By adjusting the value of the strength of the background, we can control the amount of light. We will set it as 0.5. Also, we want to change the HDR's orientation, rotate it to get different reflections and shadows. To do this, we need to add a texture coordinate node and a mapping node before the HDR image. In this specific case, the texture coordinate node isn't important, but we'll see it becomes relevant when adding the logo to the stem. The mapping node allows us to change the HDR's rotation angle. For the nodes to have any effect, they need to be connected. Connect the generated output of the texture coordinate node to the vector input of the mapping node. Then, connect the vector output of the mapping node to the vector input of the HDR image node. You'll see that nothing changes in the 3D viewport. This is because we're still using the default settings, as if the nodes we just added weren't there. Adjust the Z rotation in the mapping node, and you'll see the lighting and shadows change on the 3D object. I'm also switching the texture coordinate node's output from generated to object, but as mentioned before, it doesn't make a difference for an HDR. I then set the Z rotation value to 220 because it is a value that I find that works well for the lighting of the room. You might also notice some yellow highlights on the stem, which I find undesirable. I want a neutral white illumination. Because the HDR is an image, we can edit it. To eliminate this yellow cast, I'll add a hue/saturation node. To do this, I click Add, then navigate to Color and select Hue/Saturation. I then position the node between the HDR image and the background node. I'll reduce the saturation to 0 to achieve a completely white light. Here's the complete node setup for the HDR. To summarize, we start with a texture coordinate node, which controls how the HDR is applied, although it's not strictly necessary for HDRs. This node is then connected to the mapping node, which allows us to move, rotate, and scale the HDR. This mapping node is then connected to the HDR image node. If we wanted to switch to a different HDR, we would do it in this node. The HDR image is then connected to the hue and saturation node, which removes the yellow tint of the reflection on the stem. This node is connected to the background node, which creates the lighting and shadows and also controls their intensity. Finally, this background node is connected to the world output node, which creates the environment. Now that we're happy with our HDR, I want to add some more detail to the stem. I think the surface is still too smooth and lacks character and depth. This perfectly smooth surface doesn't look realistic enough. It's very rare to find such a perfectly smooth surface in real life. To change this, I select the stem. In the Node Editor, I switch the drop-down from World to Object to access the stem shader nodes. As you can see, the settings we entered in the Properties panel have been converted into nodes. We can see our color, roughness, and bevel. To add some character, we'll use the normal output of the bevel node. We're going to create some grain on the stem, a subtle surface texture. I hope YouTube's compression doesn't lose too much detail, as this really adds to the realism. Just like with the HDR, we'll start by adding a texture coordinate node. Click Add, then Input, then Texture Coordinate. Next, add a mapping node, Add, then Vector, then Mapping. Connect the object output of the texture coordinate node to the vector input of the mapping node. To create this grain, we'll use a noise texture node. This node procedurally generates noise on our object. To add it, click Add, then Textures, then Noise Texture. The noise texture node has various parameters that control its appearance. The most obvious one is size, which makes the effect more or less pronounced. In this case, we'll keep the settings simple. The noise texture creates this type of texture across the entire object. To convert this texture into fake geometry, we'll use a bump node. The bump node converts the different shades of white and black into bumps and dips. The darkest areas will appear as dips. To add a bump node, simply go to Add, then Vector, then Bump. Next, connect the vector output of the mapping node to the vector input of the noise texture. Then, connect the FAC output of the noise texture to the height input of the bump node. And finally, connect the normal output of the bump node to the normal input of the bevel. As you can see, the shader looks terrible. We need to adjust the bump and noise parameters to get the desired result. First, Reduce the bump strength to 0.05 instead of 1. Then increase the noise texture's roughness to 1 and the detail to 15. If YouTube's compression doesn't ruin it, you should see subtle bumps appear on the stem, making it look more realistic. You can optionally reduce the size to 2 to change the effect. For a more pronounced effect, you can change the bump value. However, be cautious, because this value is highly sensitive. Don't increase it excessively. I'm keeping the bump value at 0.05, as I want the effect to be very subtle. Everything seems fine to me. You're not required to add these details if you prefer not to. But these small details are what will really make your renders stand out as more realistic and professional. To organize my nodes, I create a frame with a label. To do this, I select the nodes I want to group and click on Node, and then join a new frame. This creates a black rectangle to contain the selected nodes. In the right-hand panel of the Node Editor, in the Label field, I can rename the frame to base_material. We're now going to add the logo to the front of the stem. As you've probably noticed, the same shader has been applied to both the front and back of the stem since the beginning. We're going to separate these materials so they're no longer linked. To do this, select the front part of the stem. In the Node Editor, at the top, you'll see a small 2. This indicates that the shader is currently being used by 2 objects. Clicking the 2 will create a new, independent shader specifically for the front of the stem. It will no longer be linked to the back shader, meaning any changes you make to this shader won't affect the back, which wasn't the case before. This allows us to add the logo only to the front of the stem. As you can see, clicking the 2 created a copy of the shader, which means we retained all the nodes we'd already set up. To keep things organized, we're going to rename this shader to stem_front by clicking on the matte text. We're going to clear some space in the Node Editor and make it larger because we're going to add some additional nodes. The logo will have its own shader, meaning we can change its color, roughness, and so on. The first step is to create a principled BSDF shader. We can reuse the existing one. To duplicate a node, select it and go to Node, then click on Duplicate. You'll notice the node stays within the frame. To remove the node from the frame, right-click on it and select Remove from Frame. This shader will be used for the logo. We're now going to import the logo. To do this, go to Add, then go to Texture, then go to Image Texture. Then click Open. In the window that opens, navigate to the location where you save the logo. A download link for the logo can be found in the description if you need. Select the logo and click Open. The image is now imported directly into the Node Editor. To see the effect, connect the color output of the image texture node to the base color input of the principled BSDF shader, and then connect the BSDF output of the principled BSDF shader to the surface input of the material output node. You can see that the logo isn't showing up. I'd like you to pay close attention during this part, as it's probably the most complex. To add this logo, we'll be using UVs. UVs are an extremely important tool in 3D shader creation. Entire books could be written on how to use them. Currently, our 3D objects don't have any UVs. We'll need to create them just for the front part of the stem. Here you can see the UVs of cubes. UVs in 3D shaders are 2D coordinates used to unwrap a 3D surface onto a 2D plane for applying textures. We'll be unwrapping only the front part of our stem. To do this unwrap, Blender has a really simple and useful tool. To find this tool, go back to the workspace layout. With the front part of the stem selected, switch from Object Mode to Edit Mode using the menu in the top left corner. From the top menu, go to Select, and then choose All. This selects all the vertices of the mesh. We're going to automatically UV unwrap this mesh. To do this, in the top menu, or header of the 3D viewport, go to UV, then Unwrap, and finally choose Smart UV Project. In the pop-up menu, leave the settings as they are and click Unwrap. To see the results of this unwrap, switch to the shading workspace. The logo is now visible, but it's all messed up. We'll manipulate the UVs to position the logo in the center of the front face. In the bottom left area, switch the workspace to UV Editor. This workspace will show our logo and the UVs we just generated. We see that the logo is projected on these UVs, but without any coherence. To remedy this, it will be necessary to move, rescale, and rotate the UVs. I ask you to be very attentive in this part, because it is a bit tricky. It is not the time to go butterfly hunting. All the points and lines of the UVs are orange. This means that they are all selected. If you want to move the UVs, you must use the shortcut G. By pressing G, you will have the possibility to change the position of the UVs. The front part of the stem is quite easy to locate in the UVs. It is the part at the bottom left. With the G key, move the UVs so that this part is in the center of the logo. The placement is better now, but there are still some issues. By default, the image texture is set to repeat, a setting used for seamless textures. In our case, we only want a single logo to be projected. In the Node Editor, change the repeat setting to clip. This will ensure that only one logo is projected. We can also see that the logo is too large. To change its size, we need to scale the UVs up. Go back to the UV Editor on the left and press S to scale all the UVs. Use the G key to reposition the UVs so the logo is centered on the stem's front face. It's getting much better. However, we can see that the logo is flipped. To correct this, we just need to rotate the UVs. Press R to activate the Rotate tool and type 180 to rotate them by 180 degrees. The rotation was successful, but the logo is now out of alignment. No problem, just use G again to put the UVs back in the correct position. You can keep making minor adjustments by combining G and S to achieve the perfect size and position. Once you're happy with the placement, you can exit Edit Mode and switch to Object Mode using the menu in the top left corner. We'll now mix the two shaders together because, while we have the logo, we've lost the details of the base material. We've lost the bevel on the sharp edges and the small bumps that add realism. To do this, click Add, then Shader, then Mix Shader. This node blends two shaders and allows the use of a mask. We'll use the logo texture as our mask. The bottom BSDF input will be for the stem's paint shader and will be plugged into the top socket of the mix shader. And the top BSDF input will be for the decal shader and will be plugged in the bottom socket of the mix shader. As a mask, we will use the alpha socket of the image and plugs it into the FAC socket of the mix shader. The logo is no longer visible, which is normal because it's the same color as the stem. To change its color, simply go to the base color setting of the top BSDF and adjust it to the desired color. Because we're using a mask and not relying on the texture's color, we can easily change the logo's color, for example, to blue or even red. Since the logo has its own shader, we can even adjust its roughness independently of the stems. You can experiment with the value to achieve the desired result. In our case, we're setting the roughness to 0.385. To add an extra touch of realism, we're going to make the logo look like it's been engraved into the stem using a laser or CNC machining. To do this, we'll first organize the Node Editor to give us some more room. Then, we'll click Add, then Vector, then Bump. Because the logo is white, we can use the image texture's color output and plug it into the bump node's height input. We then connect the bump node's normal output to the BSDF shader's normal input. This creates an embossing effect. To invert this and create a debossing effect, just check the invert option in the bump node. We now have the desired effect. We've made just a few small adjustments here, and the stem already looks much more realistic. We could spend a lot more time tweaking the shaders in the Node Editor, but for our purposes, this is already great. The final adjustment we'll make to this texturing is to darken the bolts a bit, as I find them a little too bright. To do this, simply select one of the bolts. In the Node Editor, click on the base color of the BSDF and adjust the value to make it darker. Give yourself a high five if you've made it this far, especially if this is your first time using Blender. Take a moment to appreciate your work and make sure everything looks as you intended. The texturing stage is now complete. So, we can now move on to animation. To access the animation tools, click on the animation workspace at the top of the screen. This workspace is divided into 3 areas. The right-hand area is the familiar 3D viewport. The left area displays the camera view. And the bottom area is the dope sheet, which displays the keyframes. To begin, we are going to recenter the 3D view on our object in order to see it. Select the assembly in the outliner. Then go to the View menu and click Frame Selected. Zoom out a bit so we can see the object better. The first step is to position our camera. When you open Blender, a camera is automatically created. To make the camera match your current view, open the View sidebar by clicking the small arrow on the right side of the 3D viewport. Then in the View tab, check the Camera to View option. While in Camera View, you can move the camera by navigating the viewport. To enter Camera View, press the numpad 0 key. You're now in Camera View, so what you see here is what will be rendered. Zoom and pan to achieve your desired framing for the export. Once you're satisfied with the camera's position, you can uncheck Camera to View to exit camera navigation mode and move around freely in the 3D viewport. You can rearrange your workspace for better efficiency and also close the right-hand sidebar by dragging it to the side. We'll press 0 to switch to camera view in the viewport. We're going to create the first part of the animation, which is a 360-degree rotation. The first thing we need to do is create an empty located at the center of the stem. This empty will act as our master control. Currently, the assembly rotates around the center of the hole for the fork pivot, not around the object center. That's not correct. We want it to rotate around its own center, which is why we need to create an empty. An empty is used as a primary parent object to control a group of objects. It acts as a central control point for transformations, affecting all its child objects. To create an empty object, navigate to the Add menu, then Empty, and select Plane Axis. The empty will be placed at the current location of the 3D cursor, which is centered at the origin. We'll move it to the center of the stem. First, click the blue Z-axis on the gizmo in the top right corner. This will align the viewport perpendicular to the Z-axis. There are several ways to move an empty. One way is to go to the Object menu, then Transform, and choose Move. You can freely move the empty or constrain the movement to the X-axis by pressing X. You can also use the gizmo. In the header, click the gizmo icon and enable the Move option. The gizmo will appear on the empty, allowing you to move it. Adjust the position to place the empty at the center of the stem. Once positioned, in the outliner on the right, right-click the assembly and select Hierarchy. Drag and drop the selected meshes into the desired collection to ensure all objects are within it. Next, rename the empty by pressing F2. Name it Master Stem. We'll now create a parent-child relationship between the master stem and the assembly. This will allow us to rotate the stem around its center, and this rotation will be applied to all the meshes in the assembly. To organize the outliner, we'll remove the camera from the collection by dragging and dropping it outside of the collection, leaving only the assembly and master stem within. Next, select the assembly and then the master stem while holding Control. It's important to maintain this selection order, as reversing it would make the master stem the child of the assembly, which is not the desired outcome. Then, go to Object, Next Parent, and Next Object. The outliner should now show the master stem above the assembly in the hierarchy. To verify that parenting was successful, enable the rotation gizmo in the gizmo menu and rotate around the Z-axis. You can use the shortcut R, then Z, if you prefer. I use the short Control plus Z to undo the rotation and reset it. We'll now create our first keyframe. A keyframe captures an object's properties, location, rotation, scale, at a specific point in time. Before we begin, change the bottom workspace to the timeline editor. To create the rotation animation, we'll need 2 keyframes. One will be placed at frame 1 on the timeline with a rotation value of 0 for the master stem, and a second keyframe will be placed at frame 80 with a rotation of 360 degrees for the master stem. Make sure the master stem is selected and the timeline is set to frame 1. Then, go to Object, click on Animation, then click on Insert Keyframe with Keying Set, and select Rotation in the new tab. A small yellow diamond now appears on frame 1. This marks our first keyframe, with the master stem's rotation set to 0. Now, advance the timeline to frame 80. In the Transform Properties panel on the right, set the Z rotation to 360. To insert the next keyframe, go to the Object menu, then click on Animation, and select Insert Keyframe with Keying Set, and then select Rotation. You can now scrub back to frame 1 on the timeline to see if the rotation animated correctly. The left viewport shows the camera view we previously configured. If you have a decent GPU, you can enable rendered shading to preview the animation with textures and lighting effects. After playing the animation, I see the rotation is way too fast. Before fixing it, click the small arrow next to Summary to show only one row of keyframes. Then select keyframe 80 and drag it to frame 120. Play the animation again. I think it's still a bit too fast. Let's move the keyframe to frame 140. Did you notice the animation speed isn't consistent? It starts slow, speeds up, and then slows down again. This isn't a problem for translating objects, but it is for rotation for me. This is a default Blender setting. To fix it, you need to go to the Graph Editor. Once in the Graph Editor, click Select, and then All. Then click Normalize to see the animation speed curve. You can see it starts slow, speeds up, and then slows down again. We want a straight line, so the animation has a constant speed from beginning to end. To convert this curve to a straight line, open the key menu, select Interpolation Mode, and then choose Linear. As you can see in the graph, the curve is now a straight line, meaning the rotation speed will be constant. You can play the animation to see the result. That looks good to me. We can exit the Graph Editor and go back to the timeline. We're now going to translate the forefront screws along the x-axis. Before that, in the Gizmos properties, we'll uncheck the rotation option and check the move option. Next, in the timeline, we'll move the playhead to frame 140 so the translation starts when the rotation ends. Similar to setting keyframes for the rotation, we need keyframes for the beginning and end of the translation. Select the 4 bolts while holding Shift. In the top menu, choose Object, then under Animation, select Insert Keyframe with Keying Set, and finally choose Location. This creates a keyframe that stores the bolt's position. Next, move the playhead to frame 170. Using the gizmo, translate the bolts along the x-axis by 7.2 centimeters. In the top menu, choose Object, then under Animation, select Insert Keyframe with Keying Set, and finally choose Location. By moving the playhead to frame 140 and pressing play, you can see the translation happening. The translation is a bit too fast, so I'm selecting the keyframe 170 and moving it to frame 180. That looks good now. We'll also translate the front part of the stem. We'll repeat the same process as for the bolts. However, this time, the translation will start before the bolt's translation finishes. To do this, we'll go to frame 170 and select the front part of the stem. In the top menu, choose Object, then under Animation, select Insert Keyframe with Keying Set, and finally choose Location. Next, move the playhead to frame 210, making sure the front part of the stem is selected. Then, using the gizmo, move the piece until it's almost touching the screws in the left viewport. In the top menu, choose Object, then under Animation, select Insert Keyframe with Keying Set, and finally choose Location. I think the translation is too slow. I'm selecting the keyframe at frame 210 and moving it to frame 190. I'm making several adjustments to get the result I want. I'm moving both the starting and ending keyframes of the translation. You can also adjust these to your liking. In the end, my starting keyframe is at frame 169 and my ending keyframe is at frame 198. Now we'll work on the translation of the rear bolts. I'll move the playhead to frame 195 so the translation starts before the previous one finishes. Then, I'll select the two rear bolts while holding Shift and press K to insert a keyframe, choosing location. Next, I'll move the playhead to frame 220 and using the gizmo, translate the bolts along the Y-axis. I'll then press K to insert a location keyframe. I'm rewinding the timeline to check the animation of the bolts and also to see the overall animation. As with the front part of the stem, I'm making several adjustments to the key frames by selecting and moving them to get the ideal position. During these adjustments, I would like to thank you for watching the video so far. I'd like to know which caveman made it this far. Cavemen from all over the world, please comment so I can recognize the true ones. I think the rear bolts translation is a bit too long. To modify an existing keyframe, place the playhead at the keyframe's location. Using the gizmo, move the bolts closer to the stem. Press K to create a new keyframe. This will overwrite the previous one. As you can observe, achieving a good result requires a significant amount of animation review, followed by careful adjustment of the keyframes. The animation looks good to me. Now I want the bolts to return to their original position. To do this, I first need to extend the number of available frames, as we're currently limited to 250. To increase the frame range, in the top right of the timeline, I can change the end frame value. I'll set it to 386. Since we're not cavemen, we're not going to recreate each keyframe individually. In the outliner, select all the bolts and the front part of the stem. In the timeline, you'll see all the keyframes for each mesh. Click the arrow next to Summary to collapse it into a single track. Then, select all the keyframes. Use Shift+D to duplicate them and drag the duplicates to the right. To reverse the animation, press S, then X, then type -1. This will mirror the keyframes. Finally, move the mirrored keyframes to the desired position on the timeline. Upon replaying the animation, we can see that everything works as expected, with the translation animation playing in reverse, so the parts return to their original positions. We can further refine the timing by moving the duplicated keyframes a bit to the left on the timeline. This will decrease the duration of the pause between the original animation and its reverse counterpart. One of the advantages of using keyframes is that they're non-destructive, meaning you can always revert to earlier keyframes and make adjustments. In this case, with all the meshes selected, we can see the master keyframes that control the initial rotation. By shifting all the keyframes after the rotation to the right on the timeline, we can effectively lengthen the duration of the rotation, thus making it slower. After these adjustments, we see that our animation ends at frame 358. We can adjust the animation's end frame to 358. I then move the playhead to frame 265. I notice that the stem isn't centered in the camera view, so I'll reposition the camera to center it. I select the camera in the outliner, and in the 3D view, I switch to camera view by pressing numpad 0. To make small adjustments to the camera's horizontal position, I use G, then X twice. Holding Shift allows you to make finer, more precise adjustments. I'm making fine vertical adjustments using G, then Z, and after holding Shift for fine-tuning. As you can see, it can take quite a while to make micro adjustments to get the perfect position for each element. I'm going to speed up the video a bit since this part isn't very engaging. We can now say our animation is finished, but there's still one important step: exporting the images. To do this, go to the Properties editor and click the icon that looks like a printer printing a photo. You can choose the resolution and the format of your export. As it is for a YouTube video, we keep the basic settings 1920 by 1080. To realize an export of a fixed image, you can go on the menu bar and click on Render, then on Render Image. This will create a render of your animation at the frame where is placed the cursor. The time required for rendering will be influenced by your computer's hardware capabilities, as well as the chosen export settings. These settings can have a substantial impact on the overall render time. If you want to export your image at this stage, you can click on the menu at the top, Image, then Save As. In our case, we want to export the entirety of the animation, and it is not in this window that it happens. To export the entire animation, go back to the Output Properties. In the frame range, make sure the end frame matches the last frame you want to export. You can choose a file destination for the export by clicking the small folder icon. By default, Blender saves to the temporary files, so be sure to choose a better export folder. You can also choose the export format for your images. Since we're using a transparent background, PNG is a good choice. You can also export directly to a video format, but that's a bit risky, especially if Blender crashes during the export. You'd have to start the entire export over. And finally, the last command to export your image sequence is to click on Render, then on Render Animation, and to wait the end of the export. That brings us to the end of the video. I hope you found it informative, learned something new, and that Blender seems a little less intimidating now. If not, I hope you were at least entertained. Thank you for your attention.